start the talk. I'm not sure if you've already seen it or not. Just to do a quick recap. That's basically like a half of the time is given to Simon, the speaker, and half of the time of the talk is for you to actually interact. So ask as many questions as possible because that's the way how it works. It's really just for you to interact with the speaker. I will be using that thing to measure. So on the left we have Simon. On the right clock, that's the audience. He gets like a 5-minute head start, and then he can start jumping and talking. If you don't ask questions, what will happen is that he will run out of his time, and then for 20 minutes he will be looking at you. So yeah, it's really important that just ask. All the questions are good, so please do that. With that, you're ready to go.
Okay, thank you. So what I would like to talk to you today, rather what I want to have a discussion with you today is about transducers, which are a way of composing data transformation in Clojure. But just like first to get all the technicalities out of the way. So obviously, we're going to talk about Clojure. Not going to go very deep, but still, how many of you have heard of Clojure? All of you, perfect. How many of you have used it? Oh, okay, so I'm basically talking to mostly Clojure people, but even like those who aren't, don't worry. If you have any questions, obviously just kind of jump in, and we can kind of skip all the things what Clojure is and isn't. Right. So transducers were introduced, now it's a couple of years back, and there was like a bit of a controversy when they came out because some people from the Clojure side were claiming that this is something that's kind of unique to Clojure, and then of course the programmers from the Haskell and Scala world jumped and in a couple of days demonstrated that clearly it's not just a Clojure thing, but can be done in other languages. And I do kind of agree that this is like nothing special. Actually, what for me would be the ideal outcome for you is to just kind of see how just being kind of clever about some very simple patterns, we can build very powerful abstractions. And this is something, I think kind of the core ideas behind transducers are something that you can use in any language, like, I don't know, Python or whatever. But it is like, at the same time, it probably took kind of a very dynamic language, such as Clojure, for them to come about. And that's why I like conferences like this, even though I know I'm kind of a black sheep because while I am talking about a functional programming language, it's also dynamically typed rather than everyone has a sort of high-text static typing system. But I do think that for experimenting with some ways of how we organize our code and thinking, kind of dynamic languages are a good way to just kind of bootstart your thinking, and transducers are one such example. That's why I kind of want to talk to you about them today. So to kind of have an idea of what a transducer is, it is kind of a mouthful definition would be that it is transducer decomplex the recursion mechanism, transformation, building the output and access mechanism when working with data. So kind of imagine you have some sequence of data, like here we just have a simple range of numbers from 0 to 10, or to 9, and we want to kind of transform it in some way. So what here we're doing, so this is our data and the access mechanism of how we're taking elements from data. So for instance, like if you have lazy sequence, which this is, the access mechanism is going to be different and it's going to kind of abide by the rules of being lazy rather than if it's something else. And then we have the transformation, which in this case we're just going to increment by 1. We build out the output using conjoin, which just kind of combines the elements. So essentially what we do is like we take the first element, which is going to 0, we increase it by 1, we conjoin it, meaning kind of build a new sequence out of it, so we now have 1, and then we take the next element, which is 1 again, we increment it, so we get 2, conjoin it, so we have now 1, 2, and so forth, and the transduce is the actual call that allows us to kind of, that does all this thing. And in a way, you can also view all these 4 components as essentially being kind of user-facing protocols. So like I put protocols in scare quotes because it's like this being Clojure, the only true protocol is just the call reduce. Otherwise, it's just like a convention of how you need to write your functions in order for this kind of to work. But we see that kind of like all of those are kind of they tend to be pretty simple, and it's kind of very easy also to extend them in kind of various ways. Like at this point, like this is kind of done with the very introduction. So like now it's your chance to chime and just like start jumping in. Either if you have any kind of questions or you vehemently disagree with something I say, just please tell me so. Right, so kind of we have all this, and it's kind of a, as a note, or kind of if you kind of carefully think about through all those things, is that you can see that we also get SpringFusion for free. Like SpringFusion, for those of you who don't know, is the kind of the idea that if we combine a bunch of transformations together, let's say you start with your collection of data, and then you want to kind of first filter it, and then map it, and then maybe filter it again, and so forth. So now kind of if you do this normally, you would kind of create sort of intermediary data, which is just going to crash, and performance kind of sucks. So what you want to do is, instead of just kind of combine all those transformations to one and not create all those intermediate data. And it's kind of called, usually it's called SpringFusion. Haskell does it, Scala I think does it, Common Lisp has it in the serious libraries and so forth. So, and again, here you kind of get it's the same thing. So we'll see that this talk is going to be, we're going to spend a lot of time looking at ways to combine these transducers, the ways, so it's kind of chunks of transformations together. And this is where kind of it's very convenient that we then also get SpringFusion for free, because this allows us to kind of have our cake and eat it too, in terms of having a very modular code, but at the same time can also quite performant, or very performant. Okay, so kind of some more of the definitions, just like looking at how all those things get together. So the first two parts are the transducer and the kind of final reducing function. So here, for example, we have a very simple reimplementation of a map function that we saw previously, and it's kind of a basically looks a bit maybe daunting, but essentially what we do is we take another function f, and then we return closure, which takes the second function rf, and returns a third function with 3 arities, which is the kind of the quintessential API of a transducer is going to be. So we'll have a 0 arity, which is sort of a constructor arity that produces kind of the first value in something like a fold. Then we have the 1 arity, which is the cleanup or final arity or something, is what we do with the end result. And then the kind of the step where we take some input and the result and do something with it. So kind of what you're going to notice here is that essentially it is like it's kind of turtles whatever functions all the way down, and what this thing only does is kind of passes the work to another function. So here the f is what we're going to use in maps. So the example previously we had the increment by 1 or whatever. So this is kind of the function that usually passes to f. So this is our most outer closure, and then like the rf is the reducing function. It's kind of the one to which we pass this. So this is kind of like an example of a reducing function. So we're going to see this, like this map just essentially will pass on to kind of defer to this in all cases. So here, for example, if you want to implement minimum as a reducing function, again, we need to kind of figure out some constructor value. In this case, kind of seems sensible to pick the largest possible number. So no matter with what we compare it, we're going to get that thing. Like clearly, sometimes it can get a bit kind of messy or tricky figuring out a good constructor value. Then at the end, we just kind of return what we found, and here we're essentially using the normal closure min function to do the work for us. So it's kind of like this kind of my min here is just like a wrapper around the closure min to conform to the transducer protocol. Are you still with me, even if you're not asking questions? Yes. Okay. Perfect. Right. So let's look at another kind of slightly more complex example, because it's kind of one of the nice things that this does is that, like, if you look at this, it's kind of a drop function. So the idea is that we drop the n first elements of our sequence, and so to do this, we kind of have to figure out where we are. So we kind of have to count up to end, and then we then can start releasing values. And so what we can do here, if you want to have something that's quite efficient, is you can do something very, very naughty and use volatile, which is something that's kind of in normal codes you definitely wouldn't want, especially kind of like functional programming, like functional stateless code. But here, because it's kind of completely encapsulated in the workings of the transducer, we can actually kind of afford to do that and have quite an efficient implementation. Now, obviously, this kind of is slightly uglier than it would have been if we'd used something simpler, but it does kind of allow us to have our building blocks that are kind of very efficient, and still on the outside, these things act just as pure functions would. Of course, like there are some kind of assumptions here, like in order for this to be something that you actually kind of can do, you do have to have thread isolation, which like the transduce function that comes with Clojure obviously kind of does. And you'd also kind of, if you kind of think about just the, maybe like in both cases, this kind of entire protocol is kind of, it's very simple, similar to what you would otherwise have with something like a fold or something. And it does also mean that it is quite simple, as we'll see going forward, to extend this to work in a kind of a massively parallel setting, because you can then kind of just merge the, like you can essentially produce some intermediary results and then just kind of continue merging them and build out the output. So that's kind of a nice property, but of course, if to do that, you do kind of have path independent or a commutative operation. And kind of like, actually like this pattern, like here we're using it just for efficiency gains, but it can also be used for, to just kind of make the horrible world of Java a nicer place to live. Now, Clojure is already kind of good when it comes to interfacing with Java, but like still some patterns are just kind of completely unclosure, and it's kind of hard to express them in a nice way. But it turns out that oftentimes when kind of building up things, you can wrap them up in a transducer and then kind of use it without completely forgetting about all the kind of nastities of building up the input or whatever in Java. Like in this example, we're using a rather nice library for sketch algorithms, and we've just kind of, all the kind of building up of the data structures just is wrapped up in the transducer, and then kind of just use it as we would have any other Clojure function. And we do kind of, it's easier, I guess, also to just reason about it, because you know that you don't have any side effects running loose around your code.
He's in the middle of the talk, so you really should start interacting, otherwise you will finish very early, and there is no dinner afterwards.
Okay, so moving forward. And then the next way, and I've already kind of foreshadowed this, is like the code-reduce protocol allows us to essentially, like, it's the notion of getting the next element from something. And like while until now this something tended to be just a simple kind of Clojure collection, like a vector or something. But of course, it can also be other things. Like one that kind of Clojure provides semi out of the box is Clojure async, which are kind of the same thing as Go channels, but done as a language extension to Clojure. Or you can then also, you have libraries that kind of do the same thing with Kafka streams or Sparks, RDDs, and so forth. And kind of, the nice thing is that we kind of, like for the most part, we just stay in Clojure land and can kind of move around between all those kind of different mediums without all the kind of too much ceremony to it. Like if you look at the example for the using Clojure async, it's kind of, here's a minimal example. We build a channel, one here just like for a buffer. We send some data to it, and then as we read from it, we also kind of do the transduce of just summing up all the values. Now here note that we aren't using kind of the normal Clojure transduce, but rather using a transduce that comes with async, which means kind of like this is the last component, having a different recursion mechanism which plays well or acknowledges the asynchronous nature of the async channels. The other way we can do it is that we can also essentially bind a transformation to a channel. So here we kind of pre-build this transducer part. Here we're going to just chuck away all the nils and then square the remaining, presumably, numbers. And kind of now, the thing to notice, like we can now use this X form in any kind of context. Now here it's being used with an async channel, but it can be just like we could use literally the same var, the same value. We could also pass to a normal transduce or even something running on Kafka or whatever. This is like where one part of the power of transducers stems from. It's kind of easy to move around, and it allows us much more reuse of our code. And obviously also kind of things like much easier mocking or kind of isolating things when you want to test them, because now suddenly you don't kind of have to build up all the asynchronous machinery and the entire topology, but you can just test it with a much simpler example and still kind of make sure that all your properties are as they should be. So just kind of, for completeness sake, a couple of nice libraries that, like, this one does essentially the same thing, but it's drawing from Kafka streams, and this one does the same thing on Spark. And each one kind of comes with like the both components. So each one has its own kind of notion of call reduce, so reading from this kind of data source, and then also its own version of the recursion mechanism, meaning the ability to write to set, stream, or whatever. So kind of completely move the computation there, but at the same time kind of in a very closure way. And like especially this, like if you're using Spark, like this Belak is like a super nice library, which allows you a very kind of REPL-first development, which is something that otherwise kind of Spark is lacking, and this one makes it kind of using that much more sane. We can like sometimes you also maybe want some more kind of control over the flow, and this is like oftentimes when you otherwise instead of having some nice primitive like a map or fold over your data, you kind of have to go to something more fundamental, like just a recursion or something, because you want to break at some point or something like that. But luckily, in the context of transducers, we have this notion of reduced, where we can essentially kind of signal to our recursion mechanism that we are done and just kind of continue returning this. So kind of in this case, we have a function that finds the first element conforming to a given predicate, and so essentially we just look at if the value is this, we say, okay, we found it, return this value, and kind of we're done at that point, and you don't kind of even have to realize the rest of the collection or anything, which is kind of nice. So it does enable you to work even with infinite sequences, which is like something that bears mentioning, is that transducers are more or less, as the last part we'll see a bit later, kind of eager, but you also kind of have at least some allowances to also work in a lazy context, or with just infinite sequences and so forth. Right, now we kind of come to, I guess, the meat of this talk, or the thing that I find kind of the most fascinating. Because like the stuff we've talked about now is, yes, a slight improvement in performance, yes, a slight improvement in reusability, but it's nothing kind of mind-blowing, definitely not something kind of worth talk. But the kind of just notion of how we... Yes?
Say slight improvement in performance.
Yeah.
So where does it come from?
Just like because you don't create all the intermediary data, right? So it's kind of as it's realized, like I guess the biggest benefit is if you kind of have a couple of transformations. Do you want to do one after the other? And kind of normally what would happen would be that the way kind of these lazy sequences are implemented in Clojure is kind of using chunking. So it's going to be kind of realize 46 and 46 and 46 elements and so forth, and all those kind of get generated and then transformed and again and again and again. And you create a lot of intermediary data which kind of serves no purpose, and just shuffling from one transformation to the other. While what if you're using transducers happens is that like you don't create all those intermediary values. You just like you can think of it as sort of compiling all the transformation functions into one, and just kind of gets past the data rather than creating all the intermediate values. And that kind of improves things somewhat. Yes, please.
One classical example of this being one-pass compiler, so that a stream is only passed through once.
Yes, or like another example, which is what we're using at my work is I'm just going to jump around because like finally we start having this more interactive talk. It's kind of notion of doing single pass analysis. So you have some data and you want to analyze it, and so once you're doing that, you have this kind of a rather unfortunate trade-off of either you have a library full of nice, well-defined functions like mean and sum of squares and whatever. But if you kind of do it like that, each one has to iterate through your entire data set and calculate that. So if you want to kind of compute a lot of different statistics in the same go, like in this example, we have sum, mean, standard deviation, count, the number of zeros, and so forth. Like if you either can have this spaghetti code that does all of it in one go, or the other option is that you essentially, for each one of these, kind of have to iterate through the data. While what transducers allow you to do in a quite elegant way, or composing transducers allows you to do, is to kind of do all that in the same pass. So here, what we're doing, like the RedXFuse is a library for composing transducers, and just kind of builds up this giant transducing function that does all these things as the data goes in, and then even with the final result, even kind of gets somewhat changed. So we even added the residual sum of some residual standard deviation to it. And all of this is kind of, as it's been run, all of this is done in a single pass. But if you look at kind of each of these can also be used individually in a transduce context. So we do have this kind of a very isolated functionality, which we can then freely combine, and the performance penalty for this is very, very low. Essentially, the only thing you're paying for is a couple of more function calls. And even that, like if you have a more long-running function, the GIT will essentially kind of just optimize those away. So it becomes kind of very performant. And here, like, this is where you can have massive gains in performance compared to what you would normally have, or you would have to kind of swallow your pride and just have a specific function that does exactly this kind of analysis and kind of builds up slowly the result, which is kind of much less modular. It's harder to test, it's harder to extend, and so forth. So yeah, kind of any
more?
Yeah.
But it might be quite difficult to debug, this kind of a code. So what are the strategies for
like,
that? Or?
The way I would kind of debug this is just kind of each one of these independently, and just so essentially like I have an example for it, but like if you just wanted to test mean, you just just do the simplest possible transduce identity, then kind of call just mean and test that, and only kind of so mean works right, and then you just kind of have to kind of maybe test or just trust the library that the composition works right, and you have all those kind of components that you already know that are correct. So you kind of do it piecewise rather than having to test all of it. Like maybe you still want to, like in practice, you do also probably want to test the whole thing together, especially if you're then doing things like at the end of kind of some post-processing where it might be that you aren't looking for, like you aren't careful with division by 0 or something like that. Like those kind of bugs do happen, but still like the just the surface area of what you need to test kind of massively reduces, and you can push a lot of this functionality to libraries. For instance, in Clojure, we have this lovely pixie.stats, which comes with a bunch of functions you can see here already implemented as transducers that you can just use. So in the example here, all this like the stats is that library, so we're just using mean from there, standard deviation from their count, and so forth, which is already kind of done for us, and assembling them. And like if you compare this to most other kind of numerical libraries, like you just kind of you don't have this notion of like all of them come with some form of basic discrete statistics, but you can't combine them in an efficient way. Okay.
Sorry, why are you using transducing identity there? It's just reduce or.
Yeah, this is like one of the.
Shall I ask again? No.
Yeah, I'll repeat. Like the question is like, why is this identity here, and why it's been here? If you've noticed a couple of times previously, and this is, I guess, like one of the words of how currently Clojure supports transducers, because like you always kind of it always kind of takes two parts. So if we look at kind of back at the definition thingy. Right, so you always kind of have to have both the transformation, and in this case, like in identity here stands for transformation, meaning like we don't want to do any kind of a transformation on it for our data, and then here with conjoin is usually where most of the action happens in terms of that we actually are kind of assembling some form of computation. But like it would be very nice and kind of also obvious to have a version of transduce which omits this bit, so you can just. Because it's such a common pattern if you use transducers a lot, but kind of unfortunately, it doesn't have it. Also, like if we're already kind of talking about the words of transducers, there are a couple of more worth mentioning. And so, like the other one that's kind of painful is that you can essentially, like at least with the built-in one.
Okay. So, a question about what you mentioned earlier. If you omit that bit, wouldn't that transducer just be a state machine or something?
Can you
because
unpack this a bit
I mean,
more?
at the fundamental level, a transducer is just an extension of a state machine.
Yes.
That's where it was defined originally, at least. So if you omit that map function, then it would just be a normal state machine? Or?
I think that's a kind of like I've never thought about it before. I have to admit, but now that you said it, like it does kind of make total sense to kind of view it as essentially just usually rather simple state machine, which essentially just kind of iterates for most of its part when getting new elements and then jumps to a kind of a final state in the cleanup phase. But yeah, it's a completely valid way, and you could probably kind of even express some algorithms where using state machines quite elegantly, just kind of wrapping them in the Transducer API. So like, and I guess kind of, I really love that you pointed this out, because like this is to me kind of the magic of transducers is that the more you think about them, like the less there is to them. It's just a kind of a smart way of how you essentially wrap a function in a function, or a function in a function in a function, and that's it. But if you kind of are consistent with this, and it turns out that like, if you picked a smart way to combine them, which the authors of Clojure and the libraries building on top of them did, it kind of gives you this immense flexibility of how you can kind of build up different things. Yes?
So I'm not a Clojure programmer, so some of the concepts are probably alien to me, but can you go back to the example with the, I think you are composing an object using several keys, like sum, min, SD, count, and zeros. In Clojure, how does that work? So do all the functions you are passing there, so the mean state machine, the standard deviation state machine, the count state machine, work sequentially, or can they work in parallel? How does it work exactly?
Okay. So yeah, like this is something that kind of bears emphasizing. Like, this entire kind of block here is essentially just a Clojure data structure. So this is just like a simple Clojure map with keys and then kind of functions, which also means that we can, for instance, have code that generates this part or something like that, kind of giving another dimension to what can be done with transducers. But in terms of how these are run, is that for like, if we retain this analogy with a state machine, like you would have for each step as the new data comes in, all these functions would be called. So like one element, and then like in case of how concretely they're implemented in Redux library, it's going to be one by one, so that they're going to get called in the order that they defined. Like theoretically, you could also kind of do this in parallel, although at least for me, kind of the assumption is that the cost of these functions are going to be relatively cheap. So the kind of the most of the cost of the computation is going to be just by the sheer amount of data. But it would be easy to also have a version that does this in parallel if kind of you were inclined. So though I think that it's a case where you'd quite quickly probably have problems with just synchronization and stuff like that, because you'd have to essentially at each step, you'd have to wait for all the functions to finish. So it's probably kind of a mix. Like if you want to use something vastly parallel, the strategy I would look into is to have a custom transduce that essentially kind of farms this out to multiple workers and then just combines the end results in some same way. Sort of like the same way as you would kind of do streaming analytics in something like Spark or something, but just kind of using very basic building blocks. Although probably like at this point it makes more sense to just use one of the aforementioned libraries and use something like Kafka or Spark as the medium for that, rather than rolling your own.
Can you explain what order things are going to happen? Like 0, 1, 2, 3, like 0 is going to be generated, and then each one of these things is going to run and remember its own state, etc.?
No. Yeah. So here, like this is just standing for a list of numbers, and then what's going to happen is we're going to kind of get the first number out of this list. So this is going to be 0. Here's just identity, so we don't change it anyway. And then what this does is, okay, the post complete is going to be run at the end, so we're just going to ignore it for now. So we just get this, essentially. So we're going to pass 0 to all this transducer. So it's going to get sum plus 0 is 0, and then mean is implemented as kind of count plus sum. So it's both like count's going to set to 1 and sum is going to be set to 0, standard deviation and so forth. Like all of those get the first step in parallel. So all of them all the algorithms here have to be single pass, obviously, for this to work. And there's going to be like, so here as we finish with 0, what's going to happen is that we're going to have this intermediary data structure that's going to help with partial results for all those computations, and then we're going to kind of reduce that with the next element as one comes in and so forth, kind of build up the result.
It's slower than just having each one of them doing their job. I understand that unpacking this takes time, but
this is much
changing more or less what you're doing all the time for each number.
Like you have some, like I mean, in Clojure it's like deconstructing data structures is done quite efficiently because it's a very common pattern. So you don't pay that much of a cost. But what you gain is that you do this only once. Yes, like if you would just kind of, you could write manually a version that would be faster than this, kind of to be clear. Not much, but here the delta is pretty low, pretty small, especially if you have, like, if you don't have something that's long running, it doesn't probably matter, like if it's half a second or 300 milliseconds, probably doesn't matter that much, but in things that run for slightly longer, it's just like, it's going to get optimized enough that you basically manually, like, you won't get that much benefit, and probably it makes, like, and the thing is, like, these library functions are quite optimized. So again, like, you have to be really good to kind of capture all the efficiency gains here. But if you would kind of use some very naive way of just going once through the data for each of those, like, this is obviously going to be much slower than the transducer version. So I think it's kind of a pretty happy compromise in terms of the performance you get versus the flexibility of code. I mean, at the end of the day, this is still kind of Clojure. If you want top-of-the-line performance, you're probably going to kind of approach it differently. Even like in Clojure, you're going to use something like Neanderthal that compiles to Atlas or one of those related libraries rather than something like this. So this is kind of, I think, a happy medium that oftentimes it's kind of what you want, especially working with this so-called kind of awkward size data, which is kind of not that big that it warrants like very engineering heavy approaches by having some distributed computation or going to a GPU or something like that. But at the same time, you do still kind of care about performance. Like if you aren't smart about it, you're going to wait minutes for it and kind of go for a coffee, and then those minutes become 10 minutes and so forth. Or here you can have it like in a couple of seconds, and it's kind of good enough. And also kind of the thing, like for instance, why we're using this quite a bit at Metabase, which is an open source analytics software, is because like we have this problem that we obviously people just install it on premises. And so we have no idea on what kind of a database we're going to be running in terms of size. So we have people using us with tables, a couple of 100 rows, and those with a couple of 100 billion rows. And you kind of want, for both of them, something that works. So the attractive thing with transducers is that we have pretty good understanding of just what the performance characteristics are going to be, and just kind of doing single pass analysis everywhere does allow us to kind of keep memory consumption at least somewhat sane, because otherwise you can just kind of explode if you do something stupid, which has happened in the past, I have to admit, if you have do something stupid with someone who has massive amounts of data. And that's like, I mean, even though like, it's kind of ironic because I'm espousing all those like virtues of composing transducers, but like fundamentally the reason why we started using them was for performance, to have something that's kind of both performance just in the absolute sense, and also to have something that's easier to reason about in terms of performance. Also, as mentioned previously, transducers do kind of remove the lazy aspect of aggressive Clojure, which is something that kind of, again, if you're concerned about memory consumption and stuff, oftentimes you do kind of want this. So it was those reasons, but kind of the more we start to use them, the more we also see how much nicer and cleaner the code using them is versus what we normally have.
Can you maybe explain back the example of the composed one? I'm still having a little bit hard time. So the post-complete?
Oh, sorry, yeah, we've kind of drifted off. Sorry. So, okay, so we're kind of building our results as they come in, so we kind of finally come to the last element, and then by that point, we have built a data structure that's kind of, for the sum is the sum of those, however that much is, the mean and so forth. So, like, all those values are computed. And then this gets passed into this post-complete function, which is essentially kind of analog to what in the normal definition of a transducer would be the kind of the cleanup arity, right? So this is kind of this, but in a composable or extendable way. And what we do is then kind of compute an additional statistic out of some of the, so we take the mean and we take the standard deviation, and we do this kind of normalized mean. We calculate that and add it to the result. So at the end, what we get out is a map with sum, mean, standard deviation, count, zeros, and RSD keys. And of course, like, you could also just kind of take any of this and compose it with other elements. Kind of speaking of composition, like one neat trick is that you can do stuff like this, which is, so this kind of looks weird even to me, and I've been using Clojure for like 8 years now when I first saw it. So what happens here, like if you think about it, is, okay, we call the remove, which is just kind of like filtering Clojure. with the predicate nil, and that returns a function which then gets passed plus. So the effect of this code is that we're going to first filter our data coming in and then pass it to plus. So this is kind of a bare plus that works also with nil values, which is something that you oftentimes kind of working with data you want to do. And like why this works is, if you remember, like we're looking at this definition, so because of these intermediary step. So what's happening here is that we call remove nil, or in this case, like this is map, but same principle applies. So nil is going to be kind of the f in this case, and then that returns this closure, which takes another function, and this function, the rf, is going to be, in this case, the plus. So you now can see how this works if we look at the kind of definition. So we're just kind of, essentially, we're going to defer in most cases just to plus, and so, except for the case where we actually get a new element where we do also something kind of using f. In the case of remove, it's going to be like check if the predicate returns true. In that case, don't do anything else, add it to the overall result that we've built. Are you kind of with me on that? It's kind of, I mean, it's kind of obscure, but it's also pretty elegant, and then once you kind of start using it, it's pretty kind of like it. Or kind of speaking of composition, right, the basic version is just that you've probably also seen by now. You can just, again, also compose them, and then another kind of the weird thing here, or whatever, like the non-intuitive thing here is that the order works differently than it normally would. Like in most of the rest of the closure, like the compose obviously gets resolved from right to left, like, but here, it gets left from right, or from, that's why I also like to write it one under the other, so it's kind of closer to, so it's clear what happens. So in this case, we're first filtering, and then we're doing the map. Which again is kind of, if you think it's like the side effect of how these things are defined. More questions?
Okay, so considering the name of the conference, you may want to actually name the technique.
Touché. Yes. Like in all this kind of examples, as you can see, like we do quite a bit of kind of currying the results, which I guess although this is kind of also shows like one of the words where closure is kind of not completely committed to like being fully curried or something, because you do then have this problem that because this is kind of completely valid, if oftentimes like you don't want like, so you have kind of two versions of, let's say, remove. Like one is with just one argument, which is going to return a transducer, but I could also have a version with kind of the vanilla remove, where I would also have the collection as the second argument, which would kind of do this immediately. And now kind of the obvious problem that you can then get here is that sometimes you just forget to, like you want to use the vanilla remove, and you forget to write the last argument, and everything, of course, kind of seems to work until you get some quite cryptic error message, which is already kind of a sore point for closure, and like what happened here, and it takes some time to kind of figure out the problem here. Like, clearly some type checking or something would be nice in this case, or just kind of, I mean, it is kind of convenient to have both of those, and it would, I think it's kind of the better decision to have those additional arities rather than having a different namespace or something, but it is something that can kind of randomly bite you if you're not very careful. I mean, if you're already kind of like, as you said, we are at a functional conference, let's also talk about lazy and eager evaluation. So in general, transducing is eager, which sometimes kind of you don't want. And there's a related problem to this that it might be that you're using some library which underneath the hood is using a transducer, but you can't really kind of access that, and you would want to add some additional computation to it and do it all in the same box. And here, Clojure has the function called Induction, which what it does is it binds a transformation to a collection, but it doesn't realize it. So kind of essentially, if you have something like this, where this call is unfortunately not available to us, and then what we do is like with the Induction is essentially that, oh, and I have a typo here. Should it be backtick here? So what deduction is going to do is kind of bind the map here. So every time that we want to realize this collection, it's going to be first go through the map. And this way we could at least like have a pre-processing step within this transducer that's going to be all done at once rather than in two separate steps. And kind of as a bonus or as a side functionality to this, because the transformation is rerun every time, it's therefore also kind of realized every time, and you can then hold on to the head without having explosion memory, which is nice. I mean, like, if you want a super nasty trick, you can even just say induction identity or something, and then you don't kind of have this problem of holding on to the head, but don't do that.
So we are almost at the end. Any more questions? Time for one. All right. Well, if not, then just keep on. So now there's a little break, and then the keynote will start again. They merge the rooms together.